Here we go. So yesterday we talked about distance and displacement. Today we're talking about speed and velocity. Okay? But before we do that, there's a quick detail that we need to hit. So in geometry, what's the length of a point? Like how long is a point? It's not, right? It's just like it's just a point. It doesn't have a length. It's just, okay? So a clock reading is kind of like that, but with time. Okay, think of a clock and the second hand, not that goes, but goes just kind of like a sweeping. Okay, how long is that second hand at the 12 o'clock position? Is it for a second? Is it for one Mississippi? No, it's just a moment. Okay, thanks, sir. You good? Okay. Um, so that's what this clock reading is, a moment in time. Okay, it's a point. Okay, versus a time duration. Do you remember what delta change in? Okay, so this is a change in clock reading. So this is going to be final clock reading minus initial clock reading. Typically, when we talk about time in like a story problem, or just that we're talking about a time duration. Okay, I went jogging for 20 minutes. Okay, that's a time duration. The reason I bring this up is because a lot of, I'd say half the physics textbooks out there, in my opinion, get sloppy, get lazy, and just write T instead of delta T. Okay, and this, when I was in your shoes way back in the day, that was a really confusing thing for me. I was like, what is going on? Like, and so I just want to be explicit with, and in class when we talk about time duration or amount of time, I'm going to use delta T. This is just like, hey, at 12:05 at that point in time, and then went to the passing period. It was between 12:05 and 12:10 or something like that. So it was a period of 5 minutes. Okay. So just want to throw that out there. All right. I also want to talk about ratios in a way that you might not have heard talked about. Okay. So you go fill up your gas and with 14.7 gallons, and it costs you $58.40. Okay. So this ratio of 58.4 over 14.7, we can find the answer to that with a calculator. That's easy. But what does that communicate? What is that ratio? Okay.
How much each gallon costs?
Yep. How much it costs for every 1 gallon. Does that make sense? Okay. So a way to like understand that is look at your units. Okay. Up here we have dollars. Down here we have gallons. Okay. If we were to like actually do this on a calculator, I think it's like $3 and hold on, I'm gonna cheat here. $3.97. Okay, $3.97. Okay, that's what our calculator would tell us. Okay, to understand what this ratio is saying, looking at the units, what this is saying is it costs $3.97 for every 1 gallon. See why I did that? So I just plugged that in my calculator. I got 3.97. Then I used my units, kind of like with our factor label method, like with moles to grams, grams to moles. This is that. Okay. Now, we're used to this. We're used to this ratio. Plastered all over every gas station sign. But what would happen if we, oops, oh, that's why you're looking confused. Sorry. What happens if I switch that ratio? What happens if I flip? What does that communicate? Yep. How many gallons of gas you can get for every $1. So here you have gallons, here you have dollars. This is, I can't remember, it's like 0.25 gallons for every $1. Does that make sense? Okay. So in general, what does a ratio communicate? Anytime you're dividing things, we're going to divide things a whole lot in this class. Okay. So what a ratio tells us is how much of the numerator there is for every 1 unit of the denominator. Okay. Anytime you divide something, looking at the units, you can break that down and say how much of the numerator there is for every 1 unit of the denominator. You okay with that? So something that you're very adept to doing, division, but it's kind of in a different light. Okay, you do that? Try that question. Thumbs up when you have a guess. Have a conversation. Tell them why you think so. All right. Hopefully you said C. Now, you might have been able to answer that without applying anything we just talked about. But this is the equation for average velocity. Okay. You can figure out the units of this looking at the equation. This will this is true for any and every equation you're given. Okay. Let's say you're like, this is easy. There's some measurements that are coming down the track that aren't so easy. You're like, what is that equal to? You can use, if you know the units of these, you can figure out the units of that. What's the unit for displacement? Meters. What's the unit for second? Good job. Okay. So you get meters, velocities in meters a second. That happens every time. Okay. So it's just trying to teach you some keys to like unlock some stuff. Okay. Thumbs up when you have a guess. Have a conversation. What do you say? B. You're moving 3 meters for every 1 second. Good with that? Thumbs up when you have a guess. Talk to your neighbor. Tell them why you think so. Okay. I'm hypothesizing myself. I think there's 2 popular answers. How many people say A? How many people say B? Okay, have an argument. Have a conversation. All those who said A, don't talk to other people who said A. Talk to people who said B. Everybody who said B, talk to people who said A. Tell them why. Tell them why. Okay, let me just throw that up there as a hint, maybe. Like that, specifically. That's what I'm hinting at. Correct answer is? Okay. So average velocity is equal to displacement over time. So I have final position minus initial position. On the time duration, I'm just going to leave it as delta t because I was given the time duration of 5 seconds. If I was given 2 clock readings, I'd use TF minus TI. Does that make sense? But because I was given this, I was given 2 points, 2 positions. So that's why I'm doing XF minus XI. Okay. So this is 10 yards minus 40 yards over 5 seconds. Yields what does the negative sign communicate? Direction. Okay, because velocity communicates both magnitude, how fast, and which direction. Okay, looking at this equation, can delta t be negative? Can delta t be negative? What would be true if delta t was negative? So what does that mean? You're going back in time. Okay, that might happen in Marvel movies, but in reality, that does not happen. Okay, this will always be positive. So mathematically, the sign of velocity will always be determined by the sign of displacement. Okay, which means what in real life? So if I put myself on a number line and I said to the right is positive, to the left is negative, if I'm walking this way, I have positive displacement. I also have positive velocity. If I'm walking this way, I have negative displacement. I also have negative velocity. Okay, the sign of displacement and velocity are telling you which way you are moving. Good with that? Okay, now let me just highlight something. If you miss a question as we go through here, that is a golden opportunity to learn something. Capture that on your notes. Okay, that your mind was changed. There is some information that got updated. Like, oh, really? Oh, any of that? Like, try to capture that in your notes. That's your journal entry for what you're learning. Does that make sense? Okay. So, missing a question can be a good thing, so long as it's not on a test. Okay. So, spoiler alert, I just told you all that. Tell your neighbor what the answer to that question is. Fine with physics. They just did the football lab. Everybody go same? Okay. Tell your neighbor what you think.
Yes, the vector measurement determines the direction and how much. So.
Okay. If you see magnitude, that should make you happy because it's more general, it's less specific than velocity. Okay. All you're looking for is the absolute value. Okay. The magnitude is whatever the measurement is without the direction. So in this case, the magnitude of velocity is speed. Okay. Velocity, what that is speed and the direction. The magnitude of velocity is speed. The magnitude of displacement is distance in a lot of ways. Okay, so when we say the magnitude, that's just the absolute value of that measurement. You okay with that? Thumbs up when you have an answer. Have a conversation. Tell them why. Correct answer is how many people say D as in dog? How many people say E as in elephant? Okay, so all right, so everybody's good with A, right? Okay, opposite directions based on the sign. Okay, the magnitude tells us how fast it's going. The absolute value of that tells us how fast. So this is different than in math class when we say, oh, +4 is greater than -7. Okay. The mama's going 7 meters every 1 second. The baby's going 4 meters every 1 second. So the mama's traveling faster than the baby is. They're just traveling in opposite directions. Yep. Yep. So this means mom's going this way, baby's going that way in the positive direction. Okay, great question. Good with that. So if you're learning stuff, that's when you like start. This is good. Like this is rich. Like you're like, yeah. All right. Woo. Here we go. This looks like a story problem, kids. Oh, there's much rejoicing. All right. So I'm gonna give you some time to like digest that on your own. Tourist is fishing, looks up, sees a bear 26 meters away, looking at him, deciding to make a break for it. He bolts towards the car, going 4 meters a second. While at the exact same time, the bear takes off, going 6 meters a second in the same direction, trying to catch the tourist. What is the furthest position that the tourist can be away from his car so that he reaches the car just as the bear reaches him? So, I want you to employ problem-solving tactics, things that you've learned in math class. to try to like engage in this problem. Let me just throw out this hint. Trying to do it mentally, it's gonna be rough. Like if you're not right, like that's just. So all these other questions, these are called, I call them clicker questions. These are like you can do in your head. This is not a do in your head type. So step one, I would highly recommend drawing a picture. Okay, doesn't have to be fancy. You can just draw boxes and label them things. So here's the car. Here's the dude. Here's the bear. Oh dear, that's a rough bear. Ooh. Kind of like a angry duck-billed platypus or something. Anyway, and then label stuff. And the dude's going 4 meters a second. Bear's going 6 meters a second. Like drawing out, putting, like somehow labeling everything that you know. Okay. Now, there is an intuitive way to do this problem, and then there's the hardcore way. The intuitive problem is hard to teach. You just kind of get it. Okay. And each problem has its own just get it. But then there's the hardcore, it's kind of more tried and true. This is easier to teach. I'm going to do this. I'll hit the intuitive way. But here's just the overall theme. Ready? If you have more than one thing moving, or if you have one thing moving in two different ways, anytime you have a separate motion, that needs to be captured by its own set of variables and equation. Okay, so how many things do we have moving here? Two. So I need a set of variables and an equation for each thing moving. Later in the homework tonight, you'll get parts where you have two parts of a trip. You need a set of variables for one and a set of variables for the second part of the trip. So anytime you're changing the motion, you need a set of variables and an equation. Okay, that's just big picture. Okay, so I'm going to call this the guy and the bear. Okay, the guy, right now, it's kind of nice because we only have three variables that we know of: displacement, time duration, and velocity. Ooh, here's another really important it's a subtle detail. If they don't tell you which direction is positive, my strong recommendation is make the way people are moving the positive direction. That way all your velocities are positive. Easy peasy. Okay. So So fill in as much as you can. Hopefully it'll look like this. That's our unknown. We got 4 and 6 meters a second. What do we do with the 26 meters? Is that how far the bear has to run? Does the bear stop here? So how do we incorporate 26 meters? I haven't had to think this way in a really long time. Anybody got anything? Okay. I'm gonna, for the sake of time, yeah, Emma. Beautiful. We're gonna say the displacement of the guy plus 26 meters. Does that make sense? The bear, the guy's running this far, the bear's running this far plus the 26 meters. Bear has to run that far. Okay, good as that. Now, time. So we've dealt with all the numbers they gave us. We don't have any more numbers in the story problem. Okay, but we have this idea of time. Who is running for a longer amount of time, or what is running for a longer amount of time? On your marks, get set, go. Who is running for a longer period of time, not distance? On your marks, get set, go. Ready, go, stop. Who's running for a longer period of time? Same. Not distance, but time. So we don't have a value for that, but we know that these two are equal. Okay, good with that? Now, you only have one equation at this point in time. Velocity of the guy is equal to displacement of the guy over over time of the guy. Okay. So you have an equation for that, and you have an equation for the bear. Velocity of the bear is equal to displacement of the bear over the time of the bear. You have an equation for each thing. Okay. I'm running out of room, so I'm going to bring this. Bring this up here. So velocity of the guy is 4 meters per second is equal to some displacement of the guy over time. I don't have to make it. I don't have to say guy and bear because they're the same thing. You all right with that? And then the bear, I've got 6 meters a second is equal to displacement of the guy plus 26 meters over the time. See how I did that? Okay, I just substituted in what I had right here as my list of my variables. Okay, now at this point here, that's the physics part. After that, this is just a math problem. Okay, how many unknowns do I have? These are the same. These are the same. 2. How many equations do I need in my system of equations to solve for 2 unknowns? 2. 1, 2. Okay. How you solve for this? You've got lots of options. It does not matter. Substitution, elimination, set them equivalent to each other. I don't care what. Just do it correctly. Okay. I'll run through it. I'm just shooting from the hip. I'm like, let's see. I don't like it when time is in the denominator, like fractions. Like, let's get rid of that. So what I'm going to do is I'm going to do this. So I'm not going to worry about the units. You could totally put the units in there, but I'm not going to. I'm going to multiply time on both sides. Bring time over. So now I have an expression for the displacement of the guy. And I'm going to substitute that in for here. Again, you can do this in a lot of different ways. So you have 6 is equal to 4 delta t plus 26 over delta t. Do the delta t's, can I cancel those out? Can I cancel these 2 out? So I don't have a delta t here. Oh yeah. Okay, so I'm going to bring delta t over here. So multiply delta t on both sides. So I have 6 times delta t plus, is equal to, okay, I'm just going to use the same color. 4 delta t plus 26. Bring delta t's, everybody with delta t over here. Just like if it was x. So at 2 delta t, so I subtracted 4 t delta t on both sides. It's equal to 26. And then divide by 2, 13. Is that my answer? What is that? That time. Oh, how do I find my answer? I can stick this into here. So I find 4 meters a second. So that's 252 meters. Okay with that? Now, that's a hardcore way to do it. Intuitive way. Anybody know the quick way to do it?
You get since 6 meters more than 4, would take 13 meters at a time. 13 at a time is 20 meters for the guy.
Yep. So you can do it that right. You just need to communicate what you're doing. You got a worksheet due tomorrow. Okay. If that didn't make sense, don't worry about it. Do the hardcore way.